Welcome back, class. So in this video, I want to take a little bit more mathematical look at the energetics of vaporization. So look at a couple ways that we can quantify how much energy it takes to vaporize. So when we have these high energy molecules that are lost from the liquid, go into the gas phase, right? It lowers the kinetic energy of the liquid as a whole, right? And if that energy is not drawn back into the liquid, right, we would see the temperature of that liquid decrease. Right? So what this tells me, right, is that vaporization is what we call an endothermic process. Right? So in other words, it requires energy. Right? So to get that, it has to pull the energy from someplace, right? And so it's going to pull the energy from wherever it gets it. So if you can add external energy, like from a gas stove or a flame, right? If not, it will draw it from the atmosphere or your skin, for example, when sweat evaporates off your skin. And as a result, it pulls energy out of your skin. We get a cooling sensation on our skin. Okay? Now that means if vaporization is endothermic and requires energy, that means condensation must be exothermic and releases energy. So, as we saw before, when that gas went into the liquid and condensed, right, it had to give up some of the energy to drop down to a lower kinetic energy state, a liquid. Right? So, since it requires input of energy, right, to occur, how much energy does it require? Well, this amount of energy is quantized as something called the enthalpy of vaporization, or sometimes called the heat of vaporization, which we abbreviate as the delta H sub vape, or the enthalpy of vaporization. Now, since it's an endothermic process, enthalpies of vaporization are always positive. And it's a somewhat temperature dependent. Most of the time we ignore the temperature dependency, but when it's listed in tables, you'll see that it's the enthalpy of vaporization at this temperature or that temperature. And so if we look, for example, at water, we can see that at room temperature, right, it's a little bit higher than it is at 100 degrees or at the boiling point for water. And this is pretty standard, right? It's going to take less energy if you're already at a higher temperature to boil, to get something, or to vaporize it, right? So at room temperature, we can compare. If we go to a higher temperature at the boiling point, right, these are going to be somewhat reduced because you're already at an elevated temperature. It doesn't take quite so much to get the vapor pressure up if it's already raised a little bit because you're at the higher temperature. Okay, now regardless, right, we just want to think about, we're going to compare things at the same temperature or at the relative boiling points or at room temperature. Now, we can see for all these molecules, right, there's not a whole lot of difference, right? Now, note all of these are polar molecules. And we can see, they don't take a whole lot of difference in vaporization, but the boiling points are quite different, right? And this is, again, because of the strength of those intermolecular forces, right? So things that are polar, but, not so polar, we can see, certain realm of boiling points. Water, with its hydrogen bonding, right, much higher boiling point. So we can see that influence of intermolecular forces again. And of course, as I said, the enthalpy of condensation, if we were to refer to that, is just going to be the opposite of the vaporization. So it's going to be negative, the same value but negative, whereas the enthalpy of vaporization is going to be positive. Now, We're going to do a sample calculation, but I'm going to hold off on that until a little bit later when we're going to go through a calculation, and I'll come back and point out that we're going to do that when we do that sample calculation. So one of the ways that we can get a bigger picture, right, is to look at something called a heating curve. So a heating curve tracks the temperature by the heat added for a material. And we can see sort of two big portions of a heating curve. We have what we might call diagonal portions, and where we have, lines with increasing slopes, and we have flat portions right here. So diagonal portions, and we have flat portions. So what we're seeing here is as we add heat, right, we see the temperature gradually climb, right? And that temperature increases linearly as I add heat. Right? So temperature goes up and up and up. And of course, I can calculate that by using my heat equation, right, which we've talked about already, right? Where we in calorimetry, where we look at how much we're heating up. So if we're looking at water, what's the mass of the water times its specific heat times how much we change the temperature by. Now tell how much heat it takes to do that. So if I want to calculate the heat necessary for one of these diagonal regions, so in this case to go from 20 degrees to 100 degrees, well, I can use Q to do that, right? I got my temperature change. I can know my specific heat. I know how much mass I have. I can calculate, how much heat this represents to go of this temperature change. Now, once you reach a phase change, right? So for water at 100 degrees, this is when we reach a phase change, boiling. Right? So once you reach the boiling point, all of the heat that we add now, you notice, doesn't increase the temperature. All of that heat is going into breaking down the intermolecular forces, into boiling. Right? So this is where the delta H of vaporization can come involved. And we can calculate the amount of heat by simply using the delta H of vaporization. And what we're doing here is taking N, this is the number of moles, times the delta H of vaporization, because remember this is kilojoules per mole. So if I just have 1 mole, then the Q is going to be equal to the delta H of vaporization. And in order to do that, then we can see, well, okay, how much does it take to transcend the flat part? So how much heat does it take to boil away all this water? Well, it's going to depend on how much water I have, right? And so for the flat portions, these are phase changes, right? No more temperature increase. All the energy is going into breaking intermolecular forces. Once the phase change is complete, so once I have only gas, now the temperature of that steam can start to rise again. And I could calculate how much energy it took to raise the steam from, say, 100 to 120 degrees or whatever. Again, using my Q, my standard Q equation that I would use on any of these slanty parts in the heat curve. Okay, so heating curve is one way that we can quantify how much heat it's going to take for specific changes to occur. Now, there is another way that we do this, or another sort of relationship that we look at. I'm not going to get into this in a lot of detail. I probably won't have you do calculations with this, but I did want to point it out anyway. And this is what's called the Clausius-Clapeyron Equation. And this relates vapor pressure to the heat of vaporization. And so what we need to understand is, as we saw before, right, the vapor pressure is not linear, right? So vapor pressure and temperature is not linear, right? If you double the temperature, the vapor pressure doesn't just double, right? It goes up by quite a bit more. So that relationship is not linear. However, the relationship between the logarithmic of the vapor pressure And the inverse of the temperature is a linear function. Now, with a couple notes here, right? We have to be dealing with the Kelvin temperature, so the absolute temperature. So the inverse of the absolute temperature versus the log of the vapor pressure does give us a linear relationship. Now, of course, we have a linear relationship, so that means we have the equation of a line. And in this case, the slope of the line equals the vapor pressure the negative vapor pressure, I should have the negative in there, is the negative vapor pressure divided by 8.314, which you might remember is a version of the gas constant, right? It's a version of R. Now, when you solve this equation, right, delta H of vaporization is going to be in joules per mole because of the units of our constant here. Now, so what's sort of the usefulness of this? Well, this is often used in labs when we want to determine the heat of vaporization, right? So this is an experimental way to determine the heat of vaporization from the slope of the line. So we can determine delta H experimentally by looking at the vapor pressure over a range of temperatures. And we can plot the natural log of that pressure versus the inverse of the Kelvin temperature, and the slope of that line will allow us to calculate the delta H of vaporization. Now, experimentally, that's great. But calculationally, we can also do something called a two-point equation. So we can have only just 2 data points. So if we don't have a whole experiment, right, we just have 2 data points, we can also use 2 data points to do some simple calculations here. Now, they'll be generally less precise because, of course, we only have 2 data points. But we can use 2 measurements of vapor pressure and temperature to calculate the delta H of vaporization if we wanted to. Now, more commonly, what we see is, since we can probably look up the delta H of vaporization, is that we use the 2-point equation to calculate the vapor pressure at some given temperature. So if we know the vapor pressure at one temperature, P1 and T1, and we pick another temperature, T2, we can use this equation to calculate P2. Now, a lot of times T1 is just simply our normal boiling point, right? Because that one's very easy to find the vapor pressure at that boiling point, right? We can look up in tables and we can find, oh, what's the vapor pressure at the boiling point, and that typically can become our T1, and then we can pick another temperature and determine the vapor pressure at that temperature, our T2 and our P2. So Clausius-Clapeyron is another useful equation that can allow us to understand the relationship between vapor pressure and temperature utilizing the delta H of vaporization. Now, since we're talking here about the behavior when we heat a sealed system, when we look at a sealed system and the vapor pressure, one more thing that we can add on to this is this idea of a critical point and what's called a supercritical fluid. Now, this is vaporization in a sealed container, like we saw before, to reach dynamic equilibrium, but we heat it. Now, typically this would be a very bad idea. We don't typically heat sealed containers because they can explode, build up pressure, right? So this has to be done in a very special way, very special containers, right? So not something we just do normally. But for some materials, as we heat, more vaporization will occur, and the pressure will continue to increase, right, as we heat it. Now, the density of the gas as this is occurring starts to go up, right, because we have a fixed volume, right? We can put more gas in there, so the gas molecules are closer and closer together, so the density of the gas gets higher and higher. At the same time, the density of the liquid is going down, right, because densities decrease with temperature, right, of liquids. So if I heat up the liquid, it gets less dense. The molecules move a little bit further apart. So the density of liquid starts to decrease a little bit. Once you reach a certain temperature and pressure combination, you get one phase, right? So you lose the interface between the solid and the gas phase. You develop what's called a supercritical fluid, or one phase. So you're increasing the temperature, and at some point, again, you lose the phase distinction, and you get supercritical fluid phase. The temperature at which that you have to go to produce a supercritical fluid is called the critical temperature. The corresponding pressure is the critical pressure. Now, once you're at the critical temperature or above it, you can no longer go back and forth between the phases, right? There is no gas and liquid anymore, right? You have this one phase now. So as long as you're above that temperature, there is no gas to liquid transition. So the gas cannot be condensed back to the liquid, no matter how much you change the pressure, right? You can keep pumping the pressure up, it doesn't matter, right? Because in essence, you no longer have a gas and a liquid, you have a supercritical fluid. We'll come back to this when we talk a little bit about phase diagrams, and we can look at where a supercritical liquid occurs, or supercritical fluid occurs on that phase diagram. Okay, well, this is going to wrap up our discussion of vaporization, condensations, and different aspects of that. In the next video, we're going to talk about other phase changes.